So today I'm excited to introduce Tony Huffman. He's a senior reverse engineer at Tenable Network Security. He works with the automation team. So he's been in computer security for 10 plus years, working on malware threats, exploit detection, and lots of other cool stuff. So excited to hear today about vulnerability scanning. Thanks.
I'll give it 1 second. Hello. Vulnerability scanning, how it works and why. So the whole talk is this going to be based off of is that little black box. When you run a scanner, what's going on? So who am I? He did most of the talk already on this. Name's Tony Huffman. I work as a senior, at Tenable as a senior reverse engineer on the threat automation team. Basically, it comes down to I look at malware stuff mostly and just try to automate our capability to detect threats. Other than that, like do talk at cons, podcasts, blogs, research, all the kind of stuff that anybody inside of the security industry tends to do. So what is vulnerability scanning? It's very simple. We're just detecting vulnerable versions of software on a system. If you're running a vulnerable version, we can determine whether it's exploitable, as in, is this version been known to be exploited or is it getting used by malware? And we can kind of give you a threat assessment. This oversimplification because vulnerability scanners anymore have basically expanded into a whole feature set of a whole bunch of different stuff now. So they're not just doing that, they're doing a whole bunch of other things. And this is actually what a vulnerability scanner looks more like now. This is our product called Tenable.io. This is our cloud solution. Anybody here ever hear of Nessus? All right, Nessus is kind of our core product that we come from. If you've heard of Tenable, you've probably heard of Nessus. And that's actually what we're going to be looking at. We're going to be looking at this section down here and that up there, and that has to do with vulnerability management. It has to do with checking whether you have a vulnerable version of a piece of software. So scanning basically usually looks like this. Assuming the scanners are installed, you're not installing the scanner. Usually configure the scan type. So you're going to be scanning Windows for Windows vulnerability, Linux for Linux vulnerabilities, website for web, etc. You set your targets, usually associated with the kind of scan you're doing. Hopefully you're not just doing all against all targets. That's not tuned very well. You need to be able to tune those. You run the scan, and you get some work to do. So it spits out, this is vulnerable, this needs fixed, etc. Or someone you know gets work to do. What we're looking at, what happens right there? So you click, and then you get results, but something's going on during that. So let's break down the tasks. These are the two parts we're going to be looking at, local checks and remote checks. I'm not going to be talking about these parts today. Web scanning, malware. Malware is mostly what I work with anymore, but asset tracking, vulnerability scanning deals with all these and 1,000 times more now. So let's talk about local checks. What is a local check? Local check requires credentials to be able to log into the system. That's what makes it local. We can use a standard protocol like SMB, SSH. We can communicate with the system to determine what the version of software is that you're running on a system. If you're running 4.2.8.7, we can just get in and get that version number out, and then we can compare it. Is that version what the CVE says is vulnerable? For anybody that doesn't know, CVE is the Common Vulnerability and Exposure. It's basically a list of places that have vulnerabilities, and you'll see something like CVE 2017-0128.
I was going to ask, are there any other points of reference you look at for common vulnerabilities that are
Absolutely.
updated?
Yep, we'll look at Cisco directly sometimes for the Cisco vulnerabilities. Sometimes we'll look at BugTrack. We look at BugTrack a lot. And BugTrack will have things above the CVE sometimes come in. And sometimes we get requests for things. So it's above and beyond even what we're looking at. It's just things that we're getting sent that somebody wants. So to make it a local check, what's really important is we get credentials that we can log into the system, whether that's Windows, Linux, OS X, whatever system it is. So with Windows, this is something we'll commonly do to be able to determine the version. You can do something like a WMI query to get a version of the installed software. We don't like using that for a lot of different reasons. One of the reasons is it's extremely unreliable. A lot of software doesn't actually update their version with minor patches. So they'll update a DLL and then not update their major version, so we won't see the update. So what we have to do is we have to go in and look at the files themselves to see what version of files that are vulnerable. So what we do is we go in the PE header, and we'll go look for the resource section inside the PE header. Anybody know what PE resource sections? It's a section inside of the PE file, the Windows executable file, that gives you some information about the version. The specific section that talks about the version is labeled with hex 10. We do an SMB read file. I think it's 16 bytes on that section. That gives us the version. We basically turn it from binary into ASCII, and then we just say, is that version greater or less than this? It's pretty simple. All we have to do is just be able to get that version and check against it. The whole thing is we have most of this all automated. So all you have to do is just push in the version. We can run through and say we need to get this for this piece of software. That makes it nice and quick, but this is the way that we can use credentials to be able to get that. Makes it extremely reliable too, because if you have like a DLL that's been updated, we can go check that DLL. We don't need to check the base software to be able to know whether we can check that DLL. Linux makes this very easy. With Linux, we automate basically all of our checks. RPMs, APKs, YUM files, all this kind of stuff. If you do a dash version on like APK package dash version, we can get the version actually put back to us. All we do is we SSHN, grab that, pop it back down, compare it against what we got. And it's not always that easy though. Sometimes for local checks, we have things like Cisco. When we're dealing with Cisco stuff, we can't always do a version check against the file system. If anybody's ever logged in a Cisco device, you're not really checking files directly. They don't like you accessing too much of the system from the iOS template. So what we have to do is we read the advisories, and a lot of times inside the advisories, they'll say run this command, and if you run this command and get this output, that means you're vulnerable. We just do that. It makes it simple for us. But sometimes we have things like Cold Fusion that makes it real difficult. Cold Fusion is Java-based, so we have to actually parse out part of the jar. We basically reverse engineered the Cold Fusion jar, figured out where the version was inside of, pull that out, compare that against our version. These are one of those things to where you'll have edge cases like this all over the place, and we got an entire team of people that just deals with these edge cases and making sure that we understand how to do checks for different pieces of software. All right, that was all local checks. This is remote checks. What is a remote check? A remote check means no credentials, no problem. We're not looking at logging into a system. This is what you think of when you think of someone hacking into a system. They're going to be looking at from a non-credentialed perspective. We're going to be usually communicating with the vulnerable protocol. We're not going to be using standard protocols like SMB, SSH, anything like that, unless that's the protocol that's vulnerable. So we're going to have to be dealing directly with the vulnerable protocols themselves. Libraries are nice when we're using this to be able to communicate with the protocol with the library, but most of the time we can't use them because we may need to take this specific flow through the protocol to be able to implement, flip a bit in this one location, and that's what lets us take the correct line where it's vulnerable, and the person that actually found the vulnerability either took that or used a piece of software that took that line. We need to be able to control all pieces of the communication. So that usually means we're writing most of the protocol through the situation. And then I'm going to talk a little bit about the rest of this, and this is talking about what we do when we get the vulnerability in front of us, using things like IDA and BinDef. So there's simple versions of this, and basically you send a request, you get a banner, the banner says you got version 3.5, Apache, IIS, any one of these, you see these on top of it. These are horribly unreliable because companies like to change these because they think if they change the version number on it that somebody's not going to actually hack them, because if they change that version number up, then they're still vulnerable, but people won't think that they're vulnerable. People will still try to attack you just the same whether you got that. Most of that stuff is just spraying out on the internet. So we can't use that because people change that. We also can't use that because a lot of servers won't advertise minor versions. If you get a patch to SMB and it's SMB1, it's not going to say SMB1 point da 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 all the way down to what version. You're talking to SMB1. It's just telling you that that's the protocol you're talking to. So we can't tell minor changes within these protocols. We also have issues to where sometimes libraries are updated that the protocol uses, so they don't think that that's their product. So because it's not their product, we have to look at the library itself that's being communicated, which means that you're not looking at a version, you're trying to communicate with that specific protocol within that product. So this makes things simple, but can't really use it until we have no other options, and sometimes that's just the only thing we're left with. If they do manage to change a version, sometimes we'll put those, and we specifically set those kind of scans up as being paranoid. So if you're paranoid and you want to be able to just really determine whether something's vulnerable, you can set it as paranoid, and we can say, okay, if you're paranoid, we determine based off of what we determine not reliable check that you might be vulnerable here. So the real process looks more like this. We start with research. We get a vulnerability in front of us. One of the first things we do is we read. What does the vulnerability say it is? Does it say it's a buffer overflow? Does it say heap overflow? Is it some kind of, is it a web directory transversal? What is the vulnerability? So Does it require specific configuration? Does it need to be installed with this specific configuration, but if it's not vulnerable? There was one that I was dealing with quite a few years ago. It was a NetBSD bug with a VPN server. So the NetBSD VPN server was actually configured right in the kernel, so you had to recompile the kernel with like a whole bunch of special flags with special libraries actually in the system in specific ways in order to get this vulnerability even be potentially present, which means I had to do all of that before I can even try to check whether it's vulnerable or not. So one of the things we can do with this is say, if that configuration, if we can see that that configuration isn't even set up, you're already not vulnerable because you're just not setting up on that configuration. Remotely, this means sometimes we send and it will say things like, that protocol is not enabled, that's not set up this way. So we can get communication back that tells us that something is or is not a certain way. Part of the research sometimes is setting up the software, and that means understanding how to install some of these major corporate pieces of software that they usually have people that they send in to install this stuff for you. That means sometimes the hardest part is just getting the software installed. We'll sit there for a day sometime with some hard software going, everything's configured. I've read the PDF 5 times, I'm doing exactly what it, but the thing still doesn't run. The protocol still isn't open, the port's not open. It's because they're used to sending people in. So part of the research inside of this is just trying to get the software to run. We have certain companies that are very well-known companies that give us problems. Every time we get a vulnerability, we need to set it up and deal with it. We've dealt with it enough times that we're getting better, but we've seen to where it's a very popular product, and we can't believe that most companies use this stuff. Do the advisories give us any hints? Sometimes they'll say, like, require this library. Sometimes certain companies are better about advisories than others. They'll tell us some information inside of it. Microsoft's hit and miss whether they're going to supply some information for us. And is it open source? So one of the things, if it's open source and you go grab the binary and you start pounding your head against the binary, just go look at the diff. Just go on GitHub if they're on GitHub. Go on Bitbucket, whatever location they're actually storing the open source product, and actually look at the change, because you might be able to just trace the code itself down the line and just use the change in the code. Or recompile it yourself. Maybe you can recompile that library in a minor way to actually deal with it there, and then you can determine what the changes are without having to take the reverse route. So now we got some information. One of the things that we have to do is we have to determine what the changes are. If it's not open source, that usually means diffing binaries. So what we'll do is we'll take the binary, we'll put it on a system, we'll take a snapshot, we'll clone it over, we'll patch it, and then we have the 2 different versions sitting right there. Well, now we have 2 different, we have a patched and unpatched binary. So what we do is we throw it in a product called bindiff. You get a map that looks like this that pops out. This side was the vulnerable side. This side is the patch side. The green branches, this is one function block. The green branches are the same. The red branches are the changes. The yellow branches are minor changes. If we look at this, we could say, oh, they just did a strlen compare. Well, we can see what they're checking for at that point. This gives us the capability to have those 2 different binaries and understand exactly what they did to patch it. This is the reversing part of the job, is to be able to go in and look at these pieces and understand exactly what the changes were, and then understand how that affects the protocol. Along with parallel with doing the diff is usually just figuring out the protocol as well. There's certain protocols that some of us deal with often that we know how to deal with really easily, SSH, SMB, RPC, all these different kind of protocols. Sometimes we get very strange things. Sometimes we get very, very strange things like custom risk-based systems that have like protocol that some guy wrote at a company 25 years ago that people are still using, and we have to figure out what that protocol is. It's not an RFC in any place, we just have to figure it out. But if it is an RFC, sometimes we read the RFC. Great things about RFC is they define what it should be written like. Bad thing about RFC is nobody really seems to follow them. So you go look at the RFC, it says you should send this, this, and this to be able to do it. And then you go find out that they didn't actually do that, so you have to kind of break it down from there. We look at open libraries. If the product is using an open library within itself, and that is the vulnerable thing, that goes back to don't pound your head on the desk. Go look at the open source aspect. So sometimes we can just go look at the library, and that'll give us some hints. And then that can actually tell us the whole protocol. The other part that we can look at this is, say it's an SMB bug in Windows. Samba is an open source SMB implementation. If we want to figure out some branches of communication, we can just go look at the source of Samba to figure out how they're doing it. And then we might be able to use Samba to communicate up to Windows SMB to figure out things along those lines. And sometimes we get down to where we couldn't figure out any information, so we just start sending random stuff at it and hitting breakpoints in memory just to see what's going on. And I've been in that situation multiple times. It's actually not that hard because as soon as you hit the breakpoint, you just kind of look at what the code tree looks like. And usually it's like if it has this in the first 3 bytes, then it does this. So it's usually not the biggest deal with that. It's just more of a headache, so you can't figure out all the code paths from that. And then there's diffing breakpoints. So once we start figuring out the protocol a little bit more, we go back to this area right here. And we say, OK, well, right here is where it was patched. I only really probably need to get to this area. So I'll go inside my debugger. So this is decompiler. I'll go inside the debugger. I'll set a breakpoint right in here on either the vulnerable or the patch version, depending on which one I'm communicating at that moment. And then I'll send it up. And once it hits the breakpoint, I can see what the call tree looks like to see what kind of path it took through the code. I can look at different pieces of the changes right there to see what the registers look like. And that's going to let me know kind of what the path and things that I can use along the line. So we have all this information. We kind of know what's vulnerable. We understand kind of what the exploit is. We see what the protocol is. What do we do with all that? We have to figure out a way to check for that safely. We can't use remote code execution, and we can't use DOS. We generally can't. We don't have a single one of our checks that I know of that do shellcode, remote code execution. Anybody that's not familiar with remote code execution, think about the 90s when they were talking about worms and bugs and remote code execution that way. It's basically that. Shellcode on systems, all that kind of stuff. We don't do that. We can't do that because people really don't like us randomly executing shellcode on systems, but not only that, it makes processes very unstable from that point. If we do something like a callback, so we open a port, do a callback, we can know whether it's vulnerable if we exploit it. Sometimes it's not even exploitable in a reliable enough way that we could even take that method. DOSing, it's usually easy to crash the process once we find the bug, send a few extra bytes here, the thing crashes. But one thing, if you were a company, would you like that we're crashing all of your systems and coming back going, hey, they're vulnerable? People don't like that, and we tend not to follow that path. But the other thing that we look at is no information. So if we send something out and we don't get anything back, well, it could be your firewall, your IDS, your HIP systems. It could be all these different other things that are sitting in line that are on your systems that could be blocking that packet. A HIP system by nature should be blocking a exploit. That's what its job is. So if you're scanning through a HIP system, which we usually say not to, but sometimes it happens anyways, if you're scanning through a HIP system and we send an overflow and it detects it as that overflow because that's what their job is to do, and it blocks it and we get no information back, even if they're patched, we could report them as vulnerable. So we can't use killing a system as a reliable aspect. Now again, we can't use it. Sometimes that's the only option. Sometimes the vulnerability is a DOS and nothing else was changed other than just fixing the DOS. So sometimes we have something called volatile checks. And if you run those, we might crash some systems. Those have to be specifically enabled, and you have to basically give full permission. And we usually only suggest running those if you specifically want to look for something that you know your target range against. Don't just run those wide. You don't know what's going to happen. We got customers, Amazon, Google, all this kind of stuff. Can you imagine if they scan their web server for a vulnerable Apache version and we just tore down their Apache version? It would be bad news for us. So what works? Well, sometimes we look at the protocol and the vulnerability together and we say, okay, so if you send so many bytes to it, it crashes. What happens if we send one less byte? What does the communication look like? Well, anybody that knows memory stuff, there's memory alignment issues. So sometimes if you're sending, 1020 bytes, then what you're looking at is memory alignment. So they'll pad out that extra buffer. So sometimes you won't actually hit the overflow, but the communication's expecting on coming back of a certain size. And when I go through an example, you'll see something like that. Error codes change. That happens actually. That's probably one of the more reliable ways to look at something. Is we send something, we get, if it's an overflow case, we get this error code, and if it's not the overflow case, then we get this error code. Especially when things are handled on a thread properly, to where we can actually kind of kill the thread a little bit, but kill it in a safe way. Yes.
Do you offer advice to customers, or do customers tell you, this is our threat concerns? Or do they just assume you're going to check everything, or do you tell them you need to check everything, or how does that work out for you?
A little bit in both directions. We try to check everything that's pretty common out there. We have 102,000 plugins or something like that, 103,000 I think we're up to. We got a lot of stuff. Anything that's common out there, we're checking for it. We also have the uncommon stuff that we have some people coming in saying, hey, can you check for that? Remote code executions, those we're really making sure we're covering the bases on that. But sometimes local software checks and stuff like that. For example, that NetBSD, BNC, or VPN server 1, that was a really edge case. I'm pretty sure nobody's actually using that other than like 1 or 2 people that we had actually ask for that. But generally, we're trying to cover everything. So, error codes change depending on the different. Now, one of the things with error code changes is it's got to actually change in a way that we can detect whether it's vulnerable. It can't be just an error code change when it's patched and nothing when it's vulnerable, because then that's still no information. Other changes in the same patch. So if you patch this, people like to compile a bunch of patches together and give them all at once. They change something else in the protocol, added a feature, removed a feature. We can look at that, determine whether things have been patched. String changes. If you talk to the protocol, they add an extra string between it. They change the way, the case of a string or something like that. Sometimes we can look at that. That's not the favored way, but if it's there and that's a good way, then we can do that. And then new features, maybe they'll be like, oh, there's a security bug fixed inside this, but we also gave you all these new features while we fix that security bug. Sometimes companies will do that to entice people to get the patch in. Because if you want the new feature, you've got to get the new security patch as well. And people will more likely go towards getting the feature. People like getting new features. So they're going to do that, and that's going to give them the capability to also get the patch in place. Sorry, I'm getting a drink here. So once we figured out something that we find is a good test, we have to widen our scope. If it's a Windows bug, we can't just scan Windows 7 and say it's good, we're checking for it. We have to go check 10, Vista, anything that we support, because we might find that earlier versions of Windows communicate slightly different, something different in the library. x86 versus x64, it's a different stack, could communicate different inside of that. We also look at other things, for example, SMB, we might go to Samba, because if we scan Samba, sometimes we'll scan Samba with an SMB bug and go, it's reporting as vulnerable. It should be reporting as vulnerable, and then we go look at Samba and we find out Samba's vulnerable as well. So we have to send the bug up to Samba. Or sometimes we scan Samba and it says it's vulnerable and it's just a different way that they implemented the protocol and we can't use that same path. Sometimes that means that we have to manipulate things to be able to keep that check. Sometimes that means that we have to change what our check is. All right, so this is a little bit of an example of doing a remote check using Acme's nice little 01 product. So the CVE said that sending 1025 bytes to an RPC server will crash it. That's a good CVE for us because it tells us what we need to know and it's telling us where it goes. So what we do is we install it, take a snapshot, clone it, get everything set up from that, do our research that we need to. So we diff the changes in the code path. You see a new branch, the input link, if it fails to return an error code. So basically, this is what we see, changed. So this is calling into a get length. It's comparing the return from get length against 3CF, which is 1020. And it's going to do a jump of greater than to that location. And then when we look at that new location, maybe that's an error check location that returns back on the protocol. So we see this. This is going to let us know what we can check against because we can see an error code that's actually being patched through there. Now that we know the changes, this only points to a patched version. One of the things we have to do is we have to determine where it's vulnerable. It doesn't matter if we determine if it's patched because those people don't care anyways because it's patched. We need to tell the people it's vulnerable. So we've figured out a way to actually figure out whether it's patched with the error code. And that's good. That lets us get something out at least. We can tell you whether you're patched. But we need to be able to get the capability to determine whether you're vulnerable. So what we do is we go look at the vulnerable. I can't say vulnerable today. Good day for not saying vulnerable. So we go look at the vulnerable version. I'm going to do it the rest of the time now. And we see something like this. So it's going to move the address of EDX and ECX, a bunch of other things. And what we're looking at here is we're looking at the behavior to see if something inside of that behavior gives us another way to detect. So did the patch something and also change something in the process? And what we can figure out from this is that if you send a 1021, it basically, let me see if this is the right slide. Yep, okay. So we can figure out that based off the patch version, the earlier version, based off byte alignment, what's going on is they're expecting a 1020 size packet. And what we send when we send a 1021, they append an ARPC extension on the end of it, and then we get back a .ARP. Well, we just figured out a way to send to the vulnerable server and manipulate the communication between the process. Let me slow this down a little bit to make sure it's clear. If I send 1020 packets to the vulnerable server, it's going to communicate back with what I send it, and it's going to append .ARPC to the end of it. That appending aspect to the end of it is going to tell me that our communication's working, and it's going to be whatever the goal of the server is. This is obviously a fictional server. If I send 1021 now, what I see in the return is .ARP instead of .ARPC. I just changed the way the communication works. Now in the patched version, what's going to happen when I send 1021, it's going to send me an error. And the error is going to say the packet's too large. On the vulnerable version, it's going to send me back that .ARP. Now I can just say if it's got .ARP, I should never see this, ever. Because it shouldn't be capable. If we see this, that's a weird edge case. Something else got patched, or sometimes we find to where they back patch things, to where they fix something and then they kind of unpatch something. You'll see that often. But if we see something like this, that's a weird issue. We should see this or the error. So if we see that, we know that they're vulnerable. That's a safe way to check a server to know whether it's vulnerable without having to actually exploit the vulnerability that's on it. So we write this. This is just a pseudocode. We send 1021 packet, receive back. If it's got the error code, you're good. We know that you're good on there. If we see that and we see that like .ARP not found, we can see that appending actually doesn't have all the correct data on it, so we'll report you as vuln. So if there's no clean solution, like I was saying before, sometimes we're stuck with whatever we're stuck with. Sometimes we have to DOS the server because it's better to have something rather than nothing. If we come out and we don't have a check for something, that's bad. So we want to give somebody at least the capability to scan their network and determine whether it's vulnerable or not. And if DOS is the way that we're doing that, we might have to just do that. Sometimes there's timing issues. So when the code changes, what they might do is you can't use like milliseconds inside of this. It usually has to be like seconds or minutes that change. So sometimes the timeouts might change with the new bug to prevent things like overloading on the server or something like that. So they might extend a timeout and then reply back after a certain amount of time. We can use something like that. And then there's always like the banners or the string changes or something like that. And these are kind of we couldn't figure out a really good way. They did a basic patch that didn't really do anything other than allow for us to kill the server. So we might have to go through some of those not so clean solutions. And then sometimes, this is the weird things that we run into. Sometimes their patch didn't actually patch. Like they're like, oh, we fixed it. And then we're like, no, you actually didn't. Still the same exact vulnerability exists. And now we have an issue that's really weird because we have a vulnerable server, we have a patch vulnerable server, and then they're going to be coming out with the patch to the patch vulnerable server. So now we have essentially this progression of checks that we need to be able to do that make for weird issues because that middle one still might be vulnerable in a way, but we still need to determine if it's the patch, if it's the midway patch. And for a local check, that's easy. So we just go in and check the version. Remote check, that can be difficult. Sometimes we run into a lot of extra bugs. It's one of those things like I'm looking at this protocol and I'm following this path, and then as we're following the path, we just find other bugs along the way. Crash the service and then realize that we weren't even looking at that part of the service and we still crashed that part of the service. So we'll find a lot of extra bugs. Sometimes people bury patches inside of massive updates, which means when we go back to the point where I was showing you diffing, what we're going to see is massive code changes. And we got to figure out what part of that massive code change is actually the fix, which means we're just burying our head inside of reversing for some period of time, depending on how large it is. 600 functions, we've seen thousands of functions change. Recompile an entire thing with a new library. So they went from this library to this library, which changed a massive amount of code. All right, any questions? All right. I know you guys are all students, so I just want to kind of, you have a question?
Yeah, I think something handle vulnerability testing in terms of IoT devices.
Mm-hmm.
How do you check for vulnerability?
Exactly the same way. If it's got a remote service, we'll log into it and check it. If it's got a remote protocol, if it's got a protocol it's communicating in, usually IoT devices is, webcams, whatever. If it's got a remote protocol, we communicate it and do the same exact thing. When it comes to actually checking, like having to do the diffing and all that kind of stuff, it really depends on what it is. So it's going to be some operating system it's written on top of. And sometimes we have to go and scrape that out. Sometimes we have to do manual work. Sometimes we can actually go just grab that operating system. BSD is very popular. We can go grab BSD and actually install it ourselves and deal with it. So a lot of it has to do with exactly the same process. If we got an IoT device, it's communicating over a protocol. If we're doing a remote check on it, we're just going to try to communicate over that protocol and do the same exact check. If it becomes a huge issue, it's definitely harder than dealing with Linux, OS X, Windows, and all that kind of stuff, unless it's Linux, OS X, Windows, BSD on the actual device. Printers are fun sometimes. We've had multiple printer issues that we've had to check for, which means that we're decompiling printers. We're basically grabbing the image off the systems and decompiling them and taking care of them from that point. So it's really the same exact process. It's just a little bit harder.
So how often do you check for the vulnerability?
Hey, you're having my issues. It's contagious.
How often do you check them? Like, is it like for every version update or something, or how often do you go for a check? Let's say you have a company like Google or Amazon into your system.
We check every version. If there's a patch, it's a security patch. We check every version. Now, as far as are you asking how often a customer should?
Yeah. No. I frankly didn't understand how this works. So basically, customers get to you and you check for the customers, right?
No. We create a product called Nessus, which above that security center in Tenable.io, they buy that product off of us. They have that product on-prem. They run a scan. They're going to configure a scan to check for, maybe they want to check, you know what Patch Tuesday is? Microsoft Patch Tuesday? So maybe Patch Tuesday was yesterday. Yesterday was Tuesday. Yeah, yesterday was Tuesday. So maybe Patch Tuesday was yesterday, and what they want to determine is, do they have vulnerable systems? Because supposedly they patched last night. So what they do is they set up and they're saying, okay, I want to look at all the new patches from yesterday on Patch Tuesday, and I want to be able to scan all my Windows systems to see if they all actually patched or not. So some of the features we do with that is we can also diff against your patch management system, like WSUS, SCCM, or something like that. And we'll go to SCCM or WSUS and we'll say, what does this say it's vulnerable? And then we'll scan the actual system and say there's a conflict of interest right here. This says it patched, but it's actually not patched. And we'll look at those things. But when they're running the scan, they're running it from the product, and that product is going to look and either perform a remote check or a local check to be able to determine. And that depends on the configuration. The remote checks are just going to be about those open protocols, and actually that's not going to check for nearly that much. But when you have things like Eternal Blue, which if anybody is familiar with that, that's something you want a remote check for, and we have a remote check for that. So when Eternal Blue came out, we had to get it out like that. Well, that means we had to reverse engineer it, we had to figure it out, and we had to get it out there. And when things like WannaCry and Petya and all that kind of stuff came out, we had check for the vulnerability, and one of our solutions is patch. And Eternal Blue won't have the same impact. Now, we can't prevent the phishing attack that actually came in off the headwind on that. Like, that's a different issue that needs to be taken care of. But that might be a different vulnerability. So they might send a phishing attack with a Java exploit. And that Java exploit installs on local system, and they use Eternal Blue to propagate through the rest of the network, or Adobe or whatever. That's where you want the local scan. If they're doing any kind of phishing attack, we're going to tell you whether they're going to succeed from a vulnerability perspective on that. Now, if you install the software and run it and do everything for them, we can't tell you on that necessarily, but we actually have, my team deals with a lot of that kind of stuff with malware. So if you install something that's a piece of known malware, we have certain things where we can send agents down and go, hey, that looks like malware. So that's where that part that I'm not covering, that deals with a lot of that. But when you're running the actual product itself, it's going to check either locally or remotely, depending on how you check, for those vulnerabilities in the patches. Clear? Awesome. Anything else? All right. I got just a little bit of 2 cents. If you want to get into this, write code, reverse your own code, write your own code. Keep making it bigger and keep reversing your own code. So if you want to get into doing this kind of work and dealing with it, write code. I can't stress that enough. Don't just start with the reversing aspect. You got to understand all those API calls that are getting called. You got to understand all the different libraries that are getting imported. Write code and then reverse your own code. It also becomes a lot easier if you've written it and then reverse it yourself, because you can go look at the source and you can say, oh, that's what that call tree looks like. That's the reason why that call tree is there. S2I, string to integer. If you do that, that's going to inject like it's an inline function. You're going to be like, I didn't write that function. Why is it inside there? It's because it's an inline function. It's going to actually inject in there. So if you want to get into doing some of this kind of stuff, you need to reverse your own code to be able to understand. That's one of the places to start, and write a lot of code. Do crackmes. That's actually one of the main areas that I started a long time ago. Crackmes weren't crackmes then, they were just software. But there's a lot of crackmes that are out there. You can go out, cheap cheap software as well, things that are on like CNET or File Hippo or something like that, and just look at those, reverse them, take a look at them. The crack me's are going to be things, anybody heard keygens, all those kind of things? Crack me's are basically people that have written challenges to be able to keygen their products. It's not a real product, but it teaches you how to actually reverse that kind of stuff. And it does a really good job at having to understand what's going on. Low-hanging fruit, like I said, File Hippo and all that kind of stuff. If you really want to get into doing some more challenging reverse engineering, malware. Malware is going to make it to where it's going to make your life hard because when you get in there, they don't want you reversing it. They don't want you touching that kind of stuff. So you're going to have anti-debugging, you're going to have things that are going to obfuscate, you're going to have weird techniques, you're going to be looking at something and wondering why it's doing that and then realize 3 days later that it's because your debugger is attached and they're detecting on that. So you might look at FS20s, detecting whether the PB and the PB table that's detecting that you're attached, and then those are just techniques that you're going to learn. Don't read without doing. This is something I see a lot of people that are new to this do, is they read all the books and then they never actually went out and did it. Read and do, and read and do, and read and do, and read and do. You need to read to be able to learn this kind of stuff, but don't just read. It's very easy to get engrossed about I read this book, I read this book, and I read this book without actually getting your hands on it. There's things that books can't cover, and it has to do with the learning process inside of this. Learn the tools. One of the things, this is kind of like being a carpenter. If you have a carpenter that doesn't know how to use a hammer, it's not a very good carpenter. You need to understand how to use the tools that help you in this. IDA, WinDBG, GDB. These things are going to make it to where you can actually do this. Now let me see what my time is. Hey, I'm running ahead of schedule. And I guess my 4 cents from this, if you want to get into companies like what I was just talking about, doing vulnerability stuff, GitHub. Write code and put it up on GitHub. When we get resumes, that's what we go look at. If someone puts GitHub at the top and they put we set down the resume immediately and go look at GitHub and see what they got, blogs, stuff like that. Put those up on it. Do talks, do what I'm doing right now. This is one of the ways that actually I got where I'm at, is I went out and I did talks at places, share information. You don't have to go to the biggest place and do the biggest talks at the biggest cons, go locally. You're going to meet people that way. You're going to get more information that way. That helps out a lot. Get involved somehow. If you're not the kind of person like standing up in front of a lot of people, write code and put it on GitHub. Go do some CTFs, capture the flags. Red team, blue team stuff is actually fairly easy to find online. And for example, the guy that works on my team with me, I used to run a podcast. He did a challenge on the podcast that I was on, and he did such a good job that I told him, like, hey, I kind of want to actually interview you inside here. That's how he got on. Go do stuff like that. That's going to get you exposed to people. Learn the politics of the industry, learn the buzzwords, and then forget them. Because a lot of my job, I get to hear the buzzwords all day long. That's marketing people. They get to deal with a lot of that kind of stuff. The buzzwords are things that a lot of people that are worried about this are really APT, cyber, all these kind of stuff. When I'm doing this kind of stuff, none of that's going through my mind. I'm trying to deal with the technical aspect stuff. But you're going to have to deal with it. Learn what those words are. Learn how to communicate people using those words. Be a person that solves a problem, not the person that creates. So it's real easy to be an exploit finder. It's a lot harder to actually solve the problems that make the exploits exist. So if you want to go out and just crash a bunch of systems and upload them, that's just an exploit. That's just a person that's creating a bunch of problems for a lot of people. Be a person that can actually solve these issues. Microsoft does their blue team thing, where they look for solutions and stuff like that. A lot of people criticize them for the prize essentially that they're giving out for it, that it's industry-changing standards that they're asking to implement, and they're giving them like $10,000 or something like that. But hey, it's something, and that's something that you can try to actually be part of. So be a problem fixer. That means also like write your own code, find your own bugs, and then fix your own bugs, so that when you go out and you talk to the person that has that bug, you can understand, you can sympathize with them a little bit about what maybe happened, why they actually found that, why they ended up in that situation. All right, and that's it for me.
Thanks.